Starting. Hello, and welcome to another wonderful adventure of the New York City Category Theory Seminar. Today we have Tim Hosgood. He's going to talk about loose simplicial objects, a useful shape for homotopy limits in homomorphic geometry. Okay, Tim, take it away.
Thank you. Thank you very much for the invite. Thank you, everybody, for attending at this unusual time for you guys. I've been told that I have to start with four pieces of information, which is that I was born in a small town in North Devon, which is down in the countryside in England. I did my undergraduate degree at Oxford in England. My PhD was in Marseille in France. And now I'm currently based back in Oxford. I work with the Topos Institute. That's my history. That's who I am. And I'm going to be talking today about some joint work with Cheyne Glass is one of the people who's at New Paltz. Also not mentioned on this title slide, but should be is Mahmoud Zainalian from Lehman College at City University, New York. And let me jump into the introduction then. The idea of this talk is it's kind of a haphazard, all over the place kind of talk. It's essentially that there are two stories which are very technical little theorems, and both of them have come up in my research. And if you look at them both for too many years, then you end up just drawing the same picture over and over again. And a lot of the work I'm focusing on at the moment with Cheyne is trying to figure out what is this picture we keep on drawing over and over again, and how can we formalize it, but also how is it useful? So today I'm going to have to cover quite a lot of stuff. I've opted to cover more things in less depth, which is not how I usually give talks. I'm usually quite precise in my talks, but today I've decided to do a sort of little stop tour kind of thing throughout a bunch of geometry, some homotopy theory, some higher category theory, and then to the stuff. So these are the two stories that sort of inspired the stuff I'm going to be talking about today. And if you don't know exactly what some of these things are about, don't worry, because that's what the introductory part of this talk is going to be about. So one of them is this theorem of Bousfield-Kahn, which for many people is a theorem of Hirschhorn. It's proved in Hirschhorn's fantastically in-depth book, which says if I have a cosimplicial set, and we'll talk about what these are in a minute, and it's Reedy fibrant, which is some model category kind of property, then a specific map happens to be a weak equivalence. It tells me that I can compute the homotopy limit of this guy by computing a thing called the totalisation. Okay, so what this really says, if I have some cosimplicial set and I want to take the homotopy limit, which is this very fuzzy thing and kind of hard to compute generally, there's a very nice, easy description, totalisation, which if you've ever taken like the totalization of a double complex, for example, it's entirely analogous to this. I can compute the homotopy limit by this very strict kind of construction instead. And the proof boils down, I mean, this isn't to dismiss the proof, it's an incredibly complex proof with a lot of work gone into it. But the sort of motto of it is there's a thing called the fat simplex, and we can sort of semi-strictify it into the simplex. And I put semi-strictify in scare quotes because that's a phrase I'm going to use a lot. And I'll try to define what it means towards the end. But the proof kind of boils down to there's a really big version of the simplex that we can sort of strictify down to get the normal simplex. And then the second theorem, which is one much more in geometry, so this was what my PhD was in complex geometry. This is a much more geometrical statement. It says if we have a coherent sheaf F, I've written here the real statement, which is we're actually allowed a complex with coherent cohomology. Again, we don't need to worry about that for now. It says if we have a coherent sheaf F, and again, we'll talk about what coherence means, then we can resolve it by a very nice complex of locally free sheaves on the check nerve. Okay, so this is what I'm going to spend the first third of the talk talking about, is like what this statement means, why it's surprising, why it's interesting, and all this kind of stuff. But again, without even knowing the details of this theorem, I can tell you what the proof boils down to. It's a large part of the proof was done by Green in the 1980s in his PhD thesis, and then I made it a bit more modern and tidied it up. And it boils down to saying that we can semi-strictify the barycentric subdivision to the pair subdivision. And again, pair and barycentric subdivision, I'll talk about it in a bit. But it turns out that the barycentric subdivision is strongly related to the fat simplex and the pair subdivision to the simplex. So if you draw pictures of both of these proofs, then you end up drawing the same kind of picture. What is that picture? It's these pictures. These are three pictures that I've drawn countless times over the last 3 years of my life. In age, they go from left to right. This picture on the left is one I've been drawing for a very long time, and this is the one that we will see in this geometric setting of coherent sheaves that I talked about. It's like we have a simplex in the middle, a two simplex, and then we have a bunch of one simplices that, there's always these one simplices that sit on the boundary of the two simplex, but we don't actually glue them to the two simplex. We just kind of, there's some maybe weak equivalence or isomorphism or something relating the one simplex to the two simplex. And each of these one simplices itself has a boundary, which is 2 points. And these 2 points are sort of like loosely glued on as well. So this is a very vague and abstract thing, and this is what I'm going to hope to be formalizing. But this is the picture. It's sort of like a two simplex with its skeleton glued on and its skeleton glued on, but in a loose kind of way. This picture in the middle is what it looks like if we actually do this in the category of simplicial sets. You can see, like, what does it mean to have a map from a one simplex to a one simplex? Well, it means I have two triangles here, a diagonal, I have some homotopies that fill them, and so on. Again, I'll talk about this in more detail later. And this picture on the right is a really nice one to keep in your heads throughout this whole talk, which is, say I take the two simplex, and again, all of these could be defined for any simplex, but for drawing purposes, the two simplex is easiest. Say I take the two simplex and I look at its sort of skeletal filtration or its skeletal decomposition. I have the two skeleton of the two simplex, which is just the two simplex, a triangle. Then I have the one skeleton of the two simplex, which is this hollow triangle here. Then I have the zero skeleton, which is just 3 points. I can imagine sort of putting these one after the other into a tube and gluing them along each other. So I get this prism which turns from the zero simplex into the two simplex, step by step, because zero simplex, one simplex, two simplex. I can imagine taking this and gluing it up and having this nice shape. And then, for some reason, for homotopical reason, which I'll justify, there's this really nice image of build this thing out of paper and then take a really small pair of scissors, very fine little surgical knife or whatever, and slit it down this line along here, and along this line down here, and along this line down here. And I'll have something which looks like a triangle at the bottom, and then 3 squares coming out of it, and it'll look a lot like this picture here, essentially. And there's a little skeleton to remind me that this is the skeleton up here. So these are just 3 pictures that I draw a lot. And these, I could call them loose simplices, or this is an extruded simplex. And the aim of this talk is to justify like why they come up, why they're interesting, and how we might look about formalizing what these vague pictures mean. So there are some nice consequences to all of this work. It's not just for the sake of, sort of figuring out what these pictures are. One is that between totalization and homotopy limits, which this Bousfield result already talks about, it seems like actually there's a lot of different things that sit in between all of these. A lot of different types of totalization, indexed by natural numbers, with Holim sort of being the infinity version. And just as how we know that for Reedy fibrant cosimplicial sets, this whole thing collapses with the Holim being equal to the tot, it seems like there actually might be some nice cases where maybe it only collapsed from tot up to tot 7, and then everything else after this actually happens to be a strict inclusion. A very specific geometric result that I want to talk about is really just caring about this, the inclusion of tot 0 into tot 1 and the Holim, because for a certain type of cosimplicial set, its tot 0, its tot is very classical and well understood. Its Holim is very well understood. And there's a mysterious thing called a simplicial twisting cochain, which we claim is actually the tot 1. So this has a useful application in geometry, which I'm going to talk about. And the main sort of open conjecture that motivates everything is this down here, which is a question from SGA6, actually. So it's quite an old question in geometry, and I'm going to start by talking about this. So I'm going to give like a very brief overview of coherent sheaves for those who in the audience aren't geometers, basically. And I'm going to try in a very brave, potentially foolish attempt to give a talk about coherent sheaves without defining what a coherent sheaf is, for reasons that I will explain. So this slide is just up here to say that actually what I'm going to talk about, I'm going to talk a lot about holomorphic geometry or complex analytic, we sometimes call it. What does that mean? It means I study holomorphic manifolds, so manifolds where they're copies of Cn and they're glued together by holomorphic functions, and I study the sheaf of holomorphic functions on these manifolds. However, most of what I'm talking about actually holds for arbitrary ring spaces. Sometimes we need them to be locally ringed. And this is the sort of framework which Mahmoud and I take in this paper up here. And a key point that makes this work so technical in some sense is we don't make any algebraicity assumptions. So complex geometry has gone through an interesting history of being incredibly popular in the early 20th century. So for example, even the definition of a coherent sheaf comes from complex geometry. And then once the development of schemes and functors of points and all this sort of like EGA, FGA, SGA style French approach was really developed, complex geometry sort of fell out of favor somewhat. And algebraic geometry had all of these super cool new tools that we could play with and prove really cool results. And people returned to studying complex geometry through these algebraic lenses. So there's a plethora of work about Kähler manifolds or K3 or projective schemes and lots of things like this, and there's Serre's-Gaga theorem. All of these things about analytic geometry, for example, complex analytic, which means holomorphic geometry, is really hard because you need to do analysis on top of your geometry. Whereas algebraic geometry is by no means easy, but in some senses, a little bit simpler to deal with. So a lot of complex geometry is sort of dealt with by going, what can we do in algebraic geometry and when can we apply those results in complex geometry? So what's a particularly interesting subject to study is non-algebraic complex geometry. And that's where a lot of this work I'm going to talk about is focused on. So here, I'm actually going to skip this slide very quickly. This was just in case anyone asks me about notation. All I'm going to be talking about is locally free complex analytic sheaves. So if you're happy with locally free sheaves, it's locally free sheaves. If you're happy with vector bundles, these guys are exactly holomorphic vector bundles. And if you're happy with principal bundles, then these guys are exactly principal bundles in some sense. So these are the main objects of study, is we care a lot about vector bundles. I'm going to switch between saying vector bundle and locally free sheaf quite a lot. We care a lot about vector bundles. Why? Because they turn up everywhere and because they're particularly simple to work with. They're defined in terms of these transition functions. And transition functions are great. They're what we call check data. They let you do lots of things very manually. You can compute Chern classes or general characteristic classes. You can do patching. You can do lots of really nice things with vector bundles. So vector bundles are great objects. They turn up in a lot of places, and they're very good and friendly to work with. Coherent sheaves, on the other hand, are a little bit more complicated. And this is a story that comes up a lot in category theory, right? Of vector bundles are such nice objects that the category of vector bundles is poorly behaved. So what we want to do instead is switch to a nicer behaved category where the objects are a little bit worse, but which contains the category of vector bundles. So that's what coherent sheaves are for. Coherent sheaves are a category. The category of coherent sheaves contains the category of vector bundles, but a few other guys as well. And as a category, it's much nicer, as we'll see. So I just want to point out that why I don't want to define the definition of a coherent sheaf is because the definition is somewhat delicate. For example, if you learn algebraic geometry from Hartshorne, which is somehow the canonical text, then you will have what Grothendieck and Serre would have called the wrong definition of coherence. In particular, Hartshorne's definition seems to imply that O of x is always a coherent sheaf for any ring space O of x. But this is not true. Not even for affine schemes is it true that O of x itself is coherent. In fact, in the holomorphic setting, the fact that the sheaf of holomorphic functions is itself a coherent sheaf, which, like I say, is sort of a generalization of what it means to be a locally free sheaf or a vector bundle, this is a very deep and powerful theorem of Oka. And the problem boils down to a very fair problem, which is Hartshorne only considers Noetherian schemes. And he's not wrong. He does say in a footnote that we only deal with coherent sheaves on Noetherian schemes. He doesn't explain how this would change his definitions, because obviously he doesn't have to. But in the non-Noetherian world or in the non-algebraic world, you need to be a bit more careful about how you define coherence. And large chunks of SGA6 are dedicated to studying pseudocoherence, which is a more general property. And it's incredibly lengthy and technical. And I would love to give a talk about it, but that's much more of a geometry talk. And also something that I struggle to get all the technical details of. There's a lot of open questions still remaining about this. But this is my point of why I don't want to define coherent sheaves, because if you look at Serre's FAC paper, Faisceau algébrique cohérent, if you look at the EGA, if you look at the Stacks project and Hartshorne, you will not find a consistent definition. So here are 4 non-definitions of what coherent sheaves are. So this top definition is the one that I said just a minute ago, is that vector bundles are very nice objects, but the category is bad. In particular, it's not an abelian category. You can't take co-kernels or kernels in general. The category of coherent sheaves is, in some sense, which I'm not going to make precise, sort of like the abelian closure of the category of vector bundles. It's not quite true, but it's a good moral statement to have. If I have vector bundles and I want to be able to take kernels and co-kernels, but I don't just want random infinite dimensional rank things that jump rank in crazy ways, the category of coherent sheaves is what you want. It arrives pretty naturally from a categorical point of view. Another non-definition is, if you come from the algebraic geometry world, you're probably pretty comfortable seeing the word quasi-coherent in a lot of places. And it turns out that in the analytic world, in the holomorphic world, quasi-coherence is not a good notion. It's not well behaved, arguably not even well defined. But most theorems that say quasi-coherent in the algebraic world, you put the word coherent in the analytic world, and you tend to get good analogies. This is another way of thinking about it if you're familiar with quasi-coherence, which is actually somewhat simpler than coherence. Here's not a definition, but a good property of why people care about coherence, is coherent sheaves are the sheaves that let us extend stalkwise arguments to local arguments. So the particular sort of like canonical foundational lemma of this is, if I have a sequence of coherent sheaves that is exact at some stalk, so at some point x, then there exists a neighborhood of x on which the restrictions of these coherent sheaves still form an exact sequence. So it says if I have some exactness on stalks, I get exactness on neighborhoods. This is a really useful property and sort of like the first thing you ever trot out the moment someone says your sheaf is coherent, you go, I can use this argument. And then the last non-definition, which is sort of a historical one, is coherence comes from complex geometry. And then in Serre's paper, his Faisceau algébrique cohérent, he defined algebraic coherent sheaves, coherent algebraic sheaves. But in complex geometry, they come from these theorems called Cartan's theorem A and Cartan's theorem B. And I, again, don't have time to delve into these. They're super wonderful theorems. And they imply essentially every good thing you might have seen in a course on sort of like complex geometry at some point, maybe. So for the example, if I have a holomorphic function on a closed subset of a Stein manifold, and here Stein means nice. You could think it's sort of the analog of contractible in the topological world, or the analog of affine in the algebraic world. So if I ever have a holomorphic function on a closed subset of a Stein guy, I can extend this to the whole Stein manifold. I get some sort of Nordstellensatz theorem out of Cartan's theorem A and B. I get the fact that every meromorphic function is the quotient of globally defined holomorphic functions. All of these come from the fact that O of x is coherent, it turns out. These are all consequences of sort of Oker's coherence theorem and Cartan's theorem A and B. So coherent sheaves, we care about them a lot. They're like vector bundles, but a little bit more floppy around the kind of place. So for this talk, the only definition I will give is that of perfectness. So here's a much simpler definition than the definition of coherence, which is if I have some cochain complex of sheaves of OX modules, and I assume it's bounded, then I say it's strictly perfect if it's actually a cochain complex of vector bundles, of locally free sheaves of finite rank. Okay? And then I say it's perfect if it's locally quasi-isomorphic to such a guy. So it's not true that if I'm locally quasi-isomorphic to a complex of vector bundles, then I am in particular a complex of vector bundles, because quasi-isomorphisms are kind of annoying. You can't glue things together by quasi-isos. And as we'll see, that's like a really big good and bad thing. So it's not true that every perfect thing is strictly perfect. In some cases, it is. For example, we will see that actually in certain algebraic cases, it is, and that's really useful. But perfectness is the notion that we really want to work with in the end. So it's these complexes of sheaves or OX modules that are locally just complexes of locally free sheaves. Like I say, the relationship between perfectness and coherence is actually rather subtle. And again, large chunks of SGA6 are dedicated to this. But for this talk, whenever I say coherent, I can really just pretend I'm saying perfect instead. And here, just a little caveat, this definition of strictly perfect is not the real definition. It's sort of a corollary of the definition that only holds in a locally ringed space. So it's a small footnote caveat that I have to put in because, this is a very ad hoc hand wavy talk, but I need to be precise about some things. So I really do care about locally ringed spaces. So let me just tell you a few things about coherent algebraic sheaves, which are really great. There's a bunch of theorems from SGA6 which tell me one thing in the end, my summary, or they tell me two things, which says when I work with schemes like Noetherian schemes, smooth schemes, projective schemes, any of these algebraic geometry things, coherent sheaves, I can just say a complex of coherent sheaves, pardon me, and I don't need to worry about the definition. There are two possible definitions I could give. Turns out it doesn't matter. They're both the same. And even better, actually, everything is strictly perfect anyway. So it's enough for me to just work with vector bundles. So the summary is, in the algebraic world, we started with vector bundles. They're great objects, but a poorly behaved category. So we passed to the category of coherent sheaves, which is a much better category, but the objects are kind of annoying. But it turns out if you're working over a nice enough scheme, which in practice we often are, then coherent sheaves are equivalent to just the vector bundles anyway, just complexes of them. So it basically says you fix the category of vector bundles by just taking complexes of vector bundles. So it's really nice. It means we can do lots of cool work about coherent sheaves using the hands-onness of vector bundles. However, in the analytic case, the holomorphic case, this is essentially broken in every way that it could be. It's still true that there is some relation between coherence and perfectness. So in particular, every coherent sheaf is a perfect complex when we consider it as a complex concentrated in degree 0. But it turns out there are two ways to define what we might mean by a complex of coherent sheaves. I'll say it very quickly, but we won't go into it. One thing is we could say it's a complex where in each degree we have a coherent sheaf. And another definition, which sounds weirder, but is actually in some sense very natural, is I say it's a complex of sheaves such that if I take the cohomology, I take like the image of one modulo the kernel of another, these cohomology objects are themselves coherent. Both of these definitions turn out to be equivalent in the algebraic world. They're not equivalent in the analytic world. So I can't say complex of coherent sheaves without telling you which one I mean. And it's an open problem as to whether or not they are the same or different. We only know it in dimension 1, essentially, or dimension 2. And even worse than this, in general, holomorphic vector bundles just don't exist. It's really hard for a vector bundle to be holomorphic. And in fact, there's a very famous counterexample of Voisin, or an example, which shows that some complex manifolds just basically have no holomorphic vector bundles. So we go from holomorphic vector bundles to this category of coherent sheaves, which is a way nicer category, but now we've got two bad things. One is I can't really talk about complexes of coherent sheaves because I've got to define what that means. And the other bad thing is I can't just work with vector bundles and say, oh, coherent sheaves are just complexes of vector bundles. Both of those things are broken. It's really, really bad. So in particular, the big problem that was open for quite some time, apart from sort of a generalized Grothendieck-Riemann-Roch in the analytic case, was just defining a Chern class for coherent analytic sheaves. Writing down what the first Chern class of a coherent analytic sheaf should be is hard. In the algebraic case, it's somewhat easy. You say my coherent sheaf is just a complex of vector bundles. Chern classes of vector bundles are easy because I have all my local check data, and then I just take an alternating sum. You can't do this in the analytic case. It's very sad. And so these are the two problems I said. And even if you could do that, it actually turns out that the way you normally turn check data into characteristic classes is via a thing called Chern-Weil theory. And we also can't do this because holomorphic connections essentially never exist. So the analytic world, terrible, terrible place to be. Nothing exists that you want it to exist. And this is where in the late 1970s and early 1980s, so starting about 1974, the notion of twisting cochains was introduced. And twisting cochains are really interesting piece of history because there is an NLab page for twisting cochains. And if you read the NLab page for twisting cochains, up until a year ago, it wouldn't have mentioned any of these papers on twisting. It was a long page, but it wouldn't mention any of these papers by Toledo and Tong and O'Brien, who essentially invented what we call a twisting cochain. It contained lots of other points of view. So a year ago, I edited the page to add these things. But so I want to talk a little bit about twisting cochains and what they are. So here are my guiding philosophies that I take, which are just these mottos that sort of build up how we can do this non-algebraic complex geometry. So the first thing is things that are global in the algebraic world are local in the analytic world. So what do I mean by that? I mean, it's not true that every coherent analytic sheaf can be resolved by locally free sheaves, but it's locally true. Locally, every coherent analytic sheaf can be locally resolved by locally free sheaves. Locally, holomorphic connections exist, and so on and so on. Then this other thing is, if you have a bunch of local stuff, you can actually turn it into a single global object, basically, by using the check nerve in some clever way, as we'll see. And the third observation that people make is, if you have something simplicial, you can probably consider a DG object related to it, or vice versa. So this is like a Dold-Khan, Dold-Pup kind of thing. So this is sort of the ingredients that go into motivating a lot of this work on twisting cochains. Things don't exist globally, but they do exist locally. And if things exist locally, then you can glue them together in a simplicial way to make them exist simplicially globally. And then you can do some Dold-Khan thing to get some DG stuff out of them, and you've got chain complexes, and you're probably happy. So here's sort of how you could invent the idea of what a twisting cochain is if you didn't know what a twisting cochain was but wanted to invent something. So you would sit down and you would say, what is a complex of locally free sheaves? Well, locally, it's a complex of free sheaves. That's what it means to be locally free. It means there's some cover on which this sheaf is free on each open subset. So I could intersect all of the covers for each of the sheaf, and locally I have a complex of free sheaves. And then whenever I have my free sheaves over some open subset U alpha and my free sheaves over some open subset U beta, on the intersection, I have some isomorphism. I have these transition maps, my locally free sheaves. And if you've been doing a lot of higher category theory, you might look at this and go, okay, I've got some objects and some isomorphisms. Like, here's how I can generalize this, is I could say, instead, let's take the objects and let's not now glue them together with isomorphisms. Let's glue them together with some kind of weak equivalences instead. So for example, quasi-isomorphisms. But now we need to be careful because we've glued them together with quasi-isomorphisms. So we need to worry about coherence data. Maybe these quasi-isomorphisms don't quite commute on the nose. When I compose two of them, maybe that's not exactly the same as the composite map. So I need to throw in some homotopies witnessing these quasi-isomorphisms. And then those homotopies themselves might or might not commute. So I need to throw in some extra quasi-isomorphisms, some extra homotopies, and so on and so on. So you come up with this idea of, okay, if I want to take my complex of locally free sheaves, but loosen it homotopically, well, the moment I sort of like fiddle with it a bit in dimension one, that's going to have infinite repercussions that domino fall all the way up to infinity. And I've now got a massive heap of homotopical data to work with. Thankfully, however, you can actually write down a lot of this stuff, as we'll see in a minute. So why do we care about this generalization? Well, this is the main theorem of Toledo-Tong. And I've written 1970 question mark because they have a bunch of papers starting from, I think, 74, 76, 78, 81, 84, 86. They're big ones. And they sort of refined the definition over those papers. So I'm not sure I would confidently point at one and say, this is where they prove this fact and define everything. It's sort of over a bunch of the papers. What they show is any coherent analytic sheaf can be resolved by a twisting cochain. So it can't be resolved by one of these guys, a complex of locally free sheaves, because these guys are just too strict. But if we loosen up this thing and define a weaker notion, to get these twisting cochains where things are glued together by quasi-isos and higher homotopies and higher homotopies and all of this, then now I can resolve coherent sheaves. So instead of working with complexes of locally free sheaves, I need to work with these things called twisting cochains. And then there's a sort of hidden theorem, and I call it a hidden theorem because it's in two papers that came out in the same year, my thesis and one by Xiaotong Wei, but no one really says it, but the details are there, which says that actually this works for complexes of coherent sheaves. So we don't need to worry about the details, but it's just to say that Twisting cochains are exactly what we need instead of complexes of vector bundles. We need to work with twisting cochains. Um, there's a bunch of modern work being done on them. So Wei showed in 2016 that the DG category of twisting cochains is a DG enhancement of perfect complexes. And again, remember, perfect basically means coherent. And then Mahmoud and myself showed that you can actually construct a space of twisting cochains, a true infinity one category. So it has weak equivalences of twisting cochains and it has higher equivalences between these guys and all this kind of stuff. So you can write down what a twisting cochain is. It turns out all of these like quasi-isos and higher homotopies and blah, 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 they have to satisfy this equation down here, this thing called the Morikawa equation. So although there's like infinitely much homotopical data, it turns out that you can write it down very succinctly. So you can work with these things rather beautifully. And I'm just going to point at some nice results, which are, I mean, this is a lot of words here. I don't expect people to read this. But something that's kind of key to notice is that the Morikawa equation, which is this equation which governs all of these homotopies of these things called twisting cochains, I mean, the Morikawa equation shows up everywhere. It shows up when you have flat connections. It shows up in a bunch of physics stuff, so I'm told. But a place it shows up that is of interest to category theorists is in the DG nerve. Okay, so the DG nerve is this way where I take a DG category, a category enriched over chain complexes, and I can build a simplicial set out of it. And oftentimes that'll be a Kahn complex. It'll be an infinity one category. And I can compare it to sort of like the homotopy coherent nerve and the simplicial nerve and a bunch of all these other things. And the DG nerve is, again, one of those things where I'm not going to write down a definition because if you look at Lurie, if you look at Faonte, if you look at Caradon, so Lurie's other work, you'll find the sign conventions are different in each of those papers, and actually some of them contradict each other, and it's a fun exercise in literature review to figure out who's right and who's wrong, and the answer is nobody's wrong, but somehow they all look very different. But so this is just to point out that you can actually make this really rigorous, and you can prove that twisting cochains really are somehow in bijection with guys that live in DG categories. This is a theorem of Glass, Miller, Treadler, and Zainalian in 2022, and then there are some improvements. This is a screenshot from a paper that Mahmoud and I wrote. We sort of generalize it very subtly. So in particular, we have this theorem down here, which says that Morikawa elements of this thing here, and this is essentially saying twisting cochains, are in bijection with n simplices in the DG nerve. So it's a really nice, succinct packaging of what twisting cochains are. It turns out if you like the DG nerve, you secretly like twisting cochains. They've been there all along. Okay, the next stop on this whirlwind tour is to talk about Green's resolution. So the sort of history here is that in 1980, Toledo and Tong had a PhD student called Green who published his PhD thesis very rapidly. He did some incredibly intense and complicated calculations in it, but it's a very short thesis. It doesn't have much extra content in it at all. And shortly after writing the thesis, it remained unpublished and Green left academia. So it was somewhat lost to the annals of time. In 1986, Toledo and Tong wrote a summary of it that they had published, but it only appeared as a chapter within a book. So it's also something that hasn't really received much attention at all. So let's talk about what Green's construction is about. So a key specific point of what Green's construction does is a very important result in homological algebra. Okay, so you can either view this as a consequence to the construction I'm about to talk about, or as sort of like the thing that makes it all tick and that makes it work. So this is a theorem of Green called semi-strictification. It's not called this in Green's thesis, and he doesn't actually state this theorem. That's why there's the little asterisk. But I promise you that if you read it, it's in there. So I'm not crediting this one to myself. I wrote it up and called it semi-strictification, but it's really a theorem of Green. He shows this really cool theorem of homological algebra, which is if I have two bounded complexes of free modules, and I have a quasi-isomorphism between them, then I can sort of strictify that quasi-isomorphism into a true isomorphism at the cost of adding some contractible bits. So what do I mean by that? Well, precisely, I mean, if I have this quasi-isomorphism of bounded complexes of free modules, then there exist bounded complexes of free modules, I've called them L tilde and M tilde, such that L tilde is quasi-isomorphic to L. And in fact, it's quasi-isomorphic in a very, very nice way. It's quasi-isomorphic such that it's the direct sum of L and some contractible things. So they're called elementary complexes, but they're really contractible guys. They're things that have no cohomology at all. So I modify L by adding in some contractible stuff. I modify M by adding in some contractible stuff. So my L tilde and M tilde are quasi-isomorphic to what I started with. But now L tilde and M tilde are isomorphic, strictly isomorphic. So it means I have a morphism of complexes in each degree that is invertible. This is so much stronger than being a quasi-iso. Sometimes quasi-isos don't even have real inverses. You know, they're not witnessed by like a chain homotopy inverse. So this semi-strictification result says if I'm working with bounded complexes of free modules and I have a quasi-iso, if I'm happy to carry around some extra data of these sort of contractible bits I've added, then I can actually turn everything into an isomorphism. That's really cool. So it seems like I'm jumping around, but I'm coming back to this thing. I just need to give a little definition here, which hopefully people are familiar with, but it's just of the check nerve. So what is the check nerve? It's this thing I've mentioned before. If I have some topological space, so here I have the circle, and I have some cover of that space. So here I've got the cover consisting of two open subsets, this pink semicircle and this yellow one that overlap here and here. Well, if I have that cover, then if that cover is nice enough, then really that cover should contain all of the information that the space itself had, right? And there are some words I can use to make this formal, which is sort of good covers and cofibrant resolutions and blah, 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 blah. But the idea is, okay, if the cover is just as useful and contains just as much information as the space itself, then why don't I just study the cover? And if I really want to study the cover, what does that mean? It means I need to study all of the open subsets that are in the cover. So I need to study this red and this yellow part. But I should also study how those open subsets sit inside the original space. And the way they sit inside the original space is by overlapping each other at some points. That's why it's a cover, right? They're open, so they have to overlap properly at some point. So I should study how they intersect, right? What these overlaps look like. So that's these two little green bits here. That's the intersections of the two open subsets of my cover. But then maybe it's the case that these intersections themselves intersect in certain places. They overlap somewhere. So I should study these as well, and so on and so on. And you end up building this big simplicial object called the check nerve, where you have the open subsets themselves, you have the intersections, pairwise intersections, you have these triple intersections. And like I say, if your cover is good, turns out this cover over here is not good, then studying this simplicial object is the same as studying the topological space you started with, because it turns out you've built a cofibrant resolution. A talk which I would love for somebody else to give at some seminar ever would be the definition of good. The amount of folklore surrounding what good means, where it's proven, where it's not proven, where there are proofs, but those proofs are incorrect, that good covers exist, is a mess, to be honest with you. It's a really difficult thing, especially if you care about differentiably good, topologically good, contractibly good, holomorphically good, like smoothly good. There are lots of different subtleties here. So I just want to like plant a flag and say if anyone would like to tidy up the literature on this, it would be really, really appreciated. So now let's give another big definition, which I'm going to try to brush over a lot of the details for, which is a locally free sheaf on the check nerve, or a vector bundle on the check nerve. So I've just said that if my cover is good enough, studying the check nerve, this simplicial thing built up out of the cover, should be the same as studying my space X. But I can define a vector bundle on X. So I should be able to define a vector bundle on the check nerve. So how do I do that? Well, it turns out you can do something that's, I don't want to say obvious, but sort of natural to do. I have a simplicial object. I have my check nerve. So it has, a degree 0 level, a degree 1 level, a degree 2 level. What should a vector bundle on the check nerve be? Or in general on a simplicial space? Well, it should be a vector bundle at each degree. And then I should just ask that whenever I have a face map or a degeneracy map in my simplicial object, I get a map of the vector bundles as well. So that's what this thing here says. It says I should have a sheaf on each YP, and for any map in the simplex category, I should get a map between EP and EQ. But now I just need to be a little bit careful because what does it mean to have a map between EP and EQ? Well, EP is a sheaf on YP, EQ is a sheaf on YQ, so I can't have a map directly between them. I need to push forward one or pull back the other to get a map between them. And it turns out it doesn't matter if you do push forward or pull back. And you require some sort of functoriality. So to summarize, like all I'm saying is how do I define a sheaf on the check nerve? If, I'm saying the check nerve, I can treat this as X instead. Well, I just define it at every simplicial level and I ask for it to be functorial. That's essentially it. So there are two very slick definitions you can give. You can build the Grothendieck construction of the functor that sends a space to its category of sheaves and it sends a morphism to the pullback. And then you can ask for lifts of this along your simplicial space, and this turns out to be exactly the same definition. Or you can define them as lax limit objects of the cosimplicial diagram of sheaves on the check nerve itself. So there's a bunch of like very slick definitions you can give these guys, but it's essentially a vector bundle on the check nerve is a vector bundle at each level, and it's functorial. So here's what Green's resolution does. He's facing the same problem as Toledo Tong was solving with their twisting cochains. He says, I have a coherent sheaf, it's analytic, so I can't resolve it by vector bundles. All I can do is locally resolve it by vector bundles. So this is where Toledo Tong were like, okay, great. So I locally resolve it by vector bundles, complexes of, and then I'll glue them with quasi-isos and then homotopies between those and homotopies, homotopies, homotopies. Green's thesis took a different approach. He said, okay, I know you can do that, but can I do some sort of Dold-Kahn thing? Can I turn all of your DG Murakartan looking data into something simplicial? Can I just build a global object on the nerve? Can I use these vector bundles on the check nerve in some sense? So here's what Green starts with. He says, look, I've got my complex of vector bundles over U alpha, and I've got a complex of vector bundles over U beta. Now, I know for a fact that if I restrict these vector bundles over U alpha to U alpha beta, the intersection, and I restrict the ones that live over U beta to the intersection, they're not the same thing. If they were, then my coherent sheaf would actually just be itself a vector bundle, right? The whole problem is I have local resolutions and they're not the same on intersections. If they were the same, we'd be happy and we'd be done. So this is the only interesting case to consider. He says they're not equal. But Toledo Tong told me with their twisting cochains that actually they're quasi-isomorphic. This is what Toledo Tong said. They said I can build a twisting cochain. So in particular, I can find this quasi-iso. And then he says, aha, let me use this semi-strictification result I have. Because this thing here, if I refine my cover enough, is a complex of free sheaves. This is a complex of free sheaves. They're bounded, so I can actually turn this into an isomorphism of free sheaves if I modify them both a little bit. And the way I modify them is just by adding in contractible stuff. So whatever I want to do with these guys, it's not going to see this contractible stuff, so I'm fine. So I can turn all of your sort of quasi-isomorphisms into strict isomorphisms. And then if I have three of these guys, I'm working on a triple intersection. I've got some alpha, beta, gamma. I can do it to the alpha, beta part. I can turn the quasi-iso into an iso over here. For beta, gamma, I can turn the quasi-iso to an iso. And for alpha, gamma, I can turn the quasi-iso the twisting cochain gives me into an isomorphism. But now I need to worry a little bit because okay, I still haven't defined a single thing that I can put on the alpha, beta, gamma intersection. I've got this, which is isomorphic, these two, which are isomorphic, and these two, which are isomorphic. But I know nothing about how they relate to one another. But it turns out I can apply exactly the same clever argument as in the previous step and do a very lengthy 8-page matrix calculation, as Green does in the appendix of his thesis, to show that I can actually simultaneously add more contractible bits to all of these to make all of them isomorphic now. So I start off with these three things which are not isomorphic at all. They're merely pairwise quasi-isomorphic. And if I really keep track of all my homotopies and write everything in a matrix and do some very intense calculations, I can actually show that up to contractible complements, I can make them all be isomorphic in a way that makes a triangle commute. This picture is now a picture that Mahmoud looked at for a while, and he was like, I've seen that shape before, this triangle with squares in the corner. That's called the pair subdivision. So the pair subdivision is a cubical factorization of the barycentric subdivision. So again, I'm not going to spend much time on this. Like I said, this talk is a whirlwind tour because I'm hoping that it will, I'd rather leave people with questions to ask than answer all of your questions in the talk. So you might be familiar with the barycentric subdivision. You might be familiar with this, which takes the two simplex and splits it up into six little triangles over here. The pair subdivision splits it up into four squares, like this. And it turns out that the barycentric subdivision contains a copy of the pair subdivision. So there's a great paper by Mahmood and, sorry, one co-author whose name I forget, I'm sorry, where they show a very formal result of this flavor, that somehow the barycentric subdivision sort of factors through the pair subdivision. So there's this very cool subdivision, this cubical pair subdivision. And we looked at this picture, Mahmood and I, for a long time, and we were like, yeah, I can see there's a square down here, which is this square. This is an object of, so it should label this vertex. This thing here is sort of like a one-dimensional object, right? It's a line. So it should label this point over here. This point in here, which corresponds to the two-dimensional part, well, actually, that's labeled by a two-simplex here, exactly. So maybe there's a clever way of labeling the pair subdivision with Green's construction, and we can see that Green's construction is really sort of like a clever pair subdivision trick. And this might let us prove a sort of Dold-Kahn result. This was our idea. And it turns out that it's a very hard idea to make formal. The pair subdivision is very combinatorial and kind of hard to work with. So there's still a sort of open question that we have, which is we wrote a very long paper. Well, it's about 80 pages, and it ends with a rather lackluster proof of us saying we can prove something in degree 0, but none of the higher degrees, it's very hard. So there's a lot of open questions around here. I'm not going to talk about the rest of this slide for time purposes. I want to talk about some other things. The last bit of history that I need, and I understand I'm now 45 minutes into a talk and I'm still talking about history, but maybe that's a nice change, is like I said before, so Green's thesis went unpublished, where he turned Toledo Tong's DG twisting cochain things into a simplicial thing that lived on the check nerve. So there's lots of questions about, is this a Dold-Kahn thing? How do I understand all these relations? Nobody was really looking at Green's thesis. So in 1986, Toledo and Tong wrote a summary of it. And it is, in some sense, a fantastic summary. They prove a Grothendieck-Riemann-Roch theorem, and it's beautiful. In another sense, it's a terrible summary in that if you read their summary and you read Green's thesis, it would take you roughly one PhD's worth of time to figure out how they relate to one another. And I know that because this was a lot of my PhD. It's very difficult to figure out all the pieces. But something that they do to try to fix this whole story of I've got twisting cochains, I've got these vector bundles on the nerve and coherent sheaves somewhere, how do they all actually relate? Is they go, we're going to define one thing. It's called a simplicial twisting cochain, and everything lives inside simplicial twisting cochains. Twisting cochains, they're a specific example of simplicial twisting cochains. Green's resolution, that's a specific example of a simplicial twisting cochain. Perfect complexes, that's an example. Coherent sheaves, they're an example. They put everything into this world of simplicial twisting cochains. However, they write this one summary on it and then never mention simplicial twisting cochains anywhere else. And as far as I can tell, this is the unique paper in the entire mathematical literature that mentions simplicial twisting cochains, up until Mahmood and I wrote our paper. If anyone else has ever seen these guys, I would love to hear about it. But they've really not been studied very much at all. So this really prompts the question of, okay, what can we say then? What can we say about the sort of like categorical relation between these twisting cochains, these simplicial twisting cochains, and these green complexes? What can we say about like the homotopy theory between them? What can we say instead of a Dold-Kahn approach? Is it true that this guy here is like the push out of these two guys? Is this diagram a push out diagram? Is it a pullback diagram? Is there anything we can say at all? And this brings us to the sort of last bit of technical input, which is cosimplicial sets. And again, so cosimplicial sets, what are they? Well, simplicial sets are functors from delta op into set, where delta is the simplex category. A cosimplicial set is a functor from delta into simplicial sets. So it's a functor from delta into delta op into set. Or you can think of it as like a delta times delta op into set. So these cosimplicial sets. So it's a bit like bisimplicial, but we just have an op floating around somewhere. Cosimplicial sets, kind of cool, kind of annoying to work with. That's too many dimensions to have simplicial stuff in. People are happy with simplicial sets. We love simplicial sets. Cosimplicial sets, that's a lot of indices you're going to be carrying around. So it'd be really nice if we could turn cosimplicial simplicial sets into simplicial ones, because as we will see, cosimplicial simplicial sets actually turn up quite a lot. So how can we turn them into just a simplicial set? Well, we can do this thing called totalization, which is what I mentioned right at the very beginning about the Bousfield-Kahn result. And again, I don't really want to give a definition, although I've technically given some definitions here. This one's not a definition, it's just an attitude. Um, I don't really want to give a definition. I just want to say it's a very natural way of turning a cosimplicial set into a simplicial set. For example, I kind of just probe it by the simplex itself in some sense. What does this mean? It means in cosimplicial simplicial sets, that category is enriched over simplicial sets, so it has an internal hom, and this is the cosimplicial simplicial set of the simplices all together in a row. Again, I don't really want to get into the details, but the point is totalization is a kind of natural operation that exists, and it looks a lot like totalization of a bicomplex. A very nice result is that we can write it as an equalizer. I think this might be a result of Duggar, but I'm not sure. It's definitely in his notes on the subject. We can write the totalization as an equalizer. So it's a really strict thing. We compute a limit, a one limit in a one category. Okay, we just take an equalizer of some maps, essentially. We can actually think about the totalization in a really nice way. So there's a lot of work on this. This is in the paper that I mentioned earlier, this GMTZ paper, Glass, Miller, Treadler, Zanalian. It's also been in the paper by myself and Mahmood of like, what is the totalization? Like, what does a point in the totalization look like? And there are some nice diagrams you can draw. I do not have time to fully explain them, but like, what is a point in the totalization? Well, it's kind of like a bunch of points with a bunch of one simplices between them and a bunch of two simplices between them, and everything glues together very nicely. It's a strict equalizer. So it's sort of what you'd expect. It's a strict limit. It's a bunch of stuff glued together. A specific example I can give is on the next slide, not this one. This is a lot of technical stuff that I'm going to gloss over, but it's there in case anyone asks any questions, which is like, why do we care about totalization? Turns out it's a way of computing sheafification sometimes. And this is a really cool story. You can do sheafification by totalization. This is a result of this paper, this 2022 paper. I'm not going to go into it. There's another cool thing which I won't go into, which is that a lot of work has been done on twisting cochains in the DG categories world, where people consider pre-sheafs of DG categories. Now, pre-sheafs of DG categories are good because DG categories are great, but they're bad in the sense that we often need to, they're only really pseudo pre-sheafs. We need to rectify them. There are lots of coherence issues. Simplicial pre-sheafs don't have any of these issues. So it's kind of important to know, can we switch between the simplicial pre-sheaf and DG pre-sheaf world? It turns out we can, but I'm not going to talk about this now because, again, I don't really have time to talk about this result, but there are some nice results. I want to just give an example of totalization, which is this horrible looking example here, which is something I've been thinking about a lot recently, which is if I had to give you the worst possible definition of a principal bundle, I think I would give you this one. So what does this say? Let's unravel what this definition is. So somehow I'm defining a functor that goes from a space with a choice of cover. So I could mean topological space or whatever, some kind of space with a cover, and it gives you back a simplicial set. So what do? Well, I take some group GLR of R. So this, for example, is a Lie group. I apply Yoneda to it. So now I have a pre-sheaf of Lie groups. Or I have a pre-sheaf a priori of just sets. It turns out by doing like the point-wise structure transfer, I actually get a pre-sheaf of Lie groups. So I can de-loop it now to get a pre-sheaf of one groupoids. Okay, so now I have a pre-sheaf of one groupoid. So what can I do? I can take the nerve. This will now give me a pre-sheaf of simplicial sets. Now what can I do? Well, if you give me a space with a cover, then I know I can take its check nerve, right? And its check nerve turns that cover into a simplicial set. So I can pre-compose with the opposite of the check nerve to fix some opposites. And this now gives me, here, this part gives me a pre-sheaf of cosimplicial simplicial sets. And then I can totalize. And this gives me a pre-sheaf of simplicial sets. So it's a horrible construction. It's really horrible. It says I take GLR, I Yoneda, I de-loop, I apply the categorical nerve, I pull back by the opposite of the check nerve, then I take the totalization of the resulting cosimplicial simplicial set. Horrible big construction, but what does it give me? It gives me a simplicial set. It turns out to actually give me a Kahn complex. And points in this Kahn complex are exactly principal bundles. In fact, their isomorphism classes are principal bundles. And the lines, the paths in this Kahn complex are exactly the gauge groups. They're exactly the automorphism groups. So it turns out this like big thing of totalization and check nerves and all of this or whatever is a really formal, if not rather messy way of encoding structures like vector bundles and things like this. So this is what Mahmoud and I did in our paper. We said, this guy over here, this is how you get vector bundles. This is just another way of writing it. And again, the details were all in the paper. So we were like, I see two things we could do to generalize this. I could replace the nerve by the DG nerve, or I could do something simplicial to it. If I replace the nerve by the DG nerve, I get twisting cochains. And if I do something simplicial, I get green complexes. And if I do both, we get simplicial twisting cochains. So the sort of whole summary of this thing is this ad hoc definition of simplicial twisting cochains. Turns out I can get it by just looking at totalizations of cosimplicial simplicial sets that come from a simplicial presheaf. So again, lots of details in the paper. Going to skip over them. Lots of open questions that I'm also going to skip over because now I want to, in the last like 3 to 4 minutes, actually come back to the pictures that I promised at the very beginning. So I'm going to have to talk a little bit about homotopy limits. And again, going to be super vague here. Like what is a homotopy limit? Well, here's a way of thinking about it. It's I take a limit, which sort of has two properties, right? It's like it should be a cone and it should be universal. So it should have maps into everything such that lots of things commute. That's this guy on the left here. Like a limit of this diagram downstairs should be an object that has maps into everything such that everything commutes. And it should be a universal such object. So everything else factors through it. So when I think about homotopy limits, I sort of do the same thing. I just say the word homotopy everywhere. If I want to give a hand-waving definition, I say, okay, it's an object that maps into everything, but now these triangles don't have to commute. They just need to commute up to homotopy. I just need a homotopy between this composite and this map down here. And somewhere I'm going to need some sort of two homotopy because here I've got three homotopies. And downstairs, this triangle strictly commutes. But now I have three triangles that commute up to homotopies. So it doesn't make sense to ask that the composite of those homotopies strictly commutes. I need a two homotopy governing them sort of thing. So I just replace everything by the word homotopy. And then I need to do this thing of if I loosen things in dimension one, I have to follow the dominoes all the way up and start adding homotopies everywhere to worry about coherence conditions. So here's a really specific example of a homotopy limit that I want to talk about, which is the homotopy equalizer. So the one categorical story of equalizers is this. I have two parallel arrows, F and G, and I want to find a Z such that the image of F is isomorphic to the image of G. Sorry, I'm aware of the time. I'm going to be a few more minutes. So I want to find a Z such that the image of F is equal to the image of G. So I can actually construct this in a nice pullback diagram. I have Y mapping into Y times Y via the diagonal. So it just sends Y to Y comma Y. And I have X times X mapping to Y times Y with F times G. So what will a pullback be? It'll be a thing such that if I do F and G, I should get the same as, they should land as the same point inside Y. That's what it means for Z to be a pullback of this diagram. It means that when I go into Y and then duplicate that point, so I have two things the same, that should be the same as going into X times X and doing F times G. They have to be the same. So the homotopy version of this is I just say, okay, everything happens up to homotopy now. So I still have X times X going into Y times Y with F times G. But now I don't want to land them to be the same. I want there to be a one simplex connecting them. So it turns out I can take this Y to the delta 1. A beautiful theorem tells me that this is somehow to do with the like cofibrant-fibrant factorization of the diagonal map, blah, 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 blah. I can compute this thing by a strict pullback. Wow, definitely going to skip over this slide just to get to these images that I have at the very end. So this is sort of like now the state of the art of the entire story I've just told. What do we actually understand about things right now? And here's what we currently understand is we can build the space of twisting cochains, the space of these green complexes that arise in Green's resolution, these very nice vector bundles on the nerve, the space of vector bundles and the space of simplicial twisting cochains. We can build all of these guys, and we actually can witness them as pullbacks of this big four pullbacks glued together kind of thing. And it gives us lots of information. It says, for example, what's the difference between a twisting cochain and a simplicial twisting cochain? It's exactly the difference between the equalizer and the homotopy equalizer. And what's the difference between a green complex and a simplicial twisting cochain? Well, it's when I replace isomorphisms with quasi-isos. What's the difference between a vector bundle and a twisting cochain? It's when I replace isos by quasi-isos, and so on. So I get this very nice picture. One thing we can ask is, are these arrows weak equivalences? If they are, it would solve a big conjecture. To do this, we need to look at a better understanding of like this homotopy equalizer. What does this guy actually look like? And here is where I'm actually going to skip through all of these pictures after this massive buildup, I think, which is to say, if we want to build this homotopy equalizer as a sort of strict totalization type thing, what we need to do is really understand how to build these pictures of these sort of like odd little skeletons or whatever. I do have a lot of pictures here. I'm going to skip through them though, unless someone really wants to talk about them as a question. And
Skip through them slowly so that people on the video
oh,
can
okay, sorry.
watch it.
Okay, that's fair. Sorry, yeah. So here's sort of like the picture that I've said we've seen before, and my claim is it's to do with skeletons. Um, Here you can actually look at like what is the homotopy co-limit of the skeletal filtration, and we'll see we get some annoying two-dimensional data that we don't want. So we need to get rid of this somehow because in the green story, there's actually nothing that fills these things. These squares commute strictly. So we need to get rid of some two-dimensional data somehow. This is why we call it a tot subscript 1. It's like we only want to consider up to dimension 1. And the answer is we can do that somehow. We get some nice formal theorems. This is what I mentioned at the beginning, that we're going to get a notion of totalization for every natural number, and there's some sort of squeezing theorem that might prove some stuff. The slide I really want to end on is just this one, which is the white stuff is this what we already know. We have these spaces of twisting cochains, green complexes, and simplicial twisting cochains, which all come from complex geometry. They're things that people in complex geometry really care about. And there are lots of questions in complex geometry that people don't know the answer to that this sort of approach could help with. So one thing nobody knows is, are twisting cochains and simplicial twisting cochains actually different? We don't know. So is this thing a weak equivalence or not? We don't know. That's something we can try to ask. Another thing to ask is, are simplicial twisting cochains really the common generalization of twisting cochains and green complexes? In other words, is this thing a pushout? That's something we don't know. Another question would be, okay, Green's construction, this resolution, can I actually turn it into a functor or an infinity functor in some sense? In other words, does this green arrow here exist? We also don't know. And then the big one that lots and lots of people care about is the two definitions I have of complexes of coherent sheaves. Are they equivalent or are they not equivalent? This big problem that goes back to SGA 6 that many people have written about since. We don't know. However, both definitions of complexes of coherent sheaves fit into this diagram really very nicely. And there's a chance that we can throw a bunch of model category stuff at this to sort of see what's happening in a better way. So to give like a very, very brief summary of this whirlwind tour we've all been on is you start in complex geometry, you end up drawing a lot of these pictures that look like this. You end up drawing a lot of triangles with squares inside them and pair subdivisions and all these like weird, loose homotopy dimension 1 triangles and simplices. The point of this talk is to say these things are interesting. They turn up a lot in Bousfield Kahn constructions, in general homotopy limits, in complex geometry in particular. And there's a chance of being able to study them really well. And if we do study them well, we might get some nice results back in complex geometry where we started. But we pass through this really interesting part of homotopical category theory where we're worrying about all of these higher coherence questions, and we're wondering if there are ways to alleviate them because we know it happens in practice that we don't need to worry about these higher homotopies. So sort of what does this tell us about the structure of homotopy limits in particularly nice cases? And that's it. Okay, so yes, I'll stop there. Thank you, everybody. Sorry for running over a little bit, and thank you for bearing with me through that adventure.
Thank you, thank you, thank you. Very nice. Any questions? Any discussion? It's a whole world over there. I don't have a question. I just have an analogy that's well, it's a silly analogy, but so you start off talking about these two cases where you have some type of structure, and then you kind of blow up the structure to have
Yeah,
better structure, and you get,
I'll
and
define
they're
a picture of it
quasi
again.
isomorphic, and I
Yeah.
just want to say, you take a monoidal category and you do
Hmm.
the exact opposite with that. You know what?
Yes.
You take a monoidal category and then you crunch down. You take anything that's homotopic. In other words, you take all
Mhm.
the pentagons that are assumed to commute and you shrink them to a point, and then you get a monoidal category, which
Mhm.
a strict monoidal category, which is then quasi-isomorphic or monoidally equivalent, whatever.
Yeah.
So it's the exact opposite picture, and you get much better structure if you with the strict monoidal
Exactly.
category.
So I think one way of like seeing what that analogy means here is the same thing is true in this complex geometry world where you have all this twisting cochain stuff and there's a bunch of higher homotopy stuff and you want to sort of semi-strictify it. I keep on saying semi-strictify instead of strictify because there's some technical conditions and you want to strictify it. That part of the story is still the same. I think what I'm trying to highlight here is in order to do that, we kind of need to understand what these bigger blown up structures look like because it just so happens in complex geometry that maybe because of some duality, it's kind of the opposite, where the big blown up structures are a lot easier to understand and get our hands on. So that's what a lot of this work is. It's on formalizing what do these bigger blown up structures look like? And can we place them in such a way that we can see how to collapse them down? And that's sort of what this picture on the left says is this guy here, I can see very easily how to homotope this down to the two simplex. I just shrink all of these dotted arrows, but it just so happens that this shape is exactly the shape of the big loose stuff that I had floating around beforehand. So, pardon me, I think your analogy is very accurate. It's just that, yeah, in geometry, it's weird that we understand the big blown up one much, much better than we do the stricter version in some sense. And that's odd for sure.
Yeah, yeah, it's fascinating. The whole thing is um, right. I mean, I wish right now I just see it as a backwards analogy, but I mean, it would
Yeah.
be interesting to see if somehow if there's something truer about it.
It it very much would. It very much would. Unfortunately, I don't have anything. Like I say, we're just starting to understand what this looks like in the specific case of complex geometry where we know what the answers should be. To actually get a good categorical understanding of what these like loose simplicial structures might look like. So for example, one thing you can do, which I didn't mention, but is now a purely categorical thing to say is okay, let's instead of considering like a two simplex, let's consider this thing instead. It's a two simplex, and my two simplex normally has, I have face maps that give me back these one simplexes on the edges. What if it weren't the case that, for example, the face maps of my two simplex gave me exactly the faces of that two simplex? What if they gave me just some other one simplices that I had lying around instead? In other words, what if instead of a simplicial object, I had an object which had two simplices and had one simplices, but those one simplices weren't exactly the boundary of those two simplices. They were sort of like lax versions of this. They weren't isomorphic, they were just morphisms pointing in one direction. So you get this notion of sort of like a lax simplicial object. And then you can start asking about the lax homotopy limit of these kind of guys. And I think there's a lot of interesting category theory to be done here, but we're barely at the stage where we can write down formal definitions in this specific example, So there's definitely a lot of stuff here that I would like to know on a sort of like pure category theory level. Um,
Yeah.
yeah.
So another analogy, okay, and this is probably closer to what you just said, is this concept of categorification. In other words, you have
Mhm.
a structure, and then you blow it up, and you blow up each part of it, and you put it all together, and then you
Mhm.
have some better acting, better behaving, better properties type of structure that's
Yeah.
more useful, and that's a categorification.
Yeah, exactly. Yeah, and it's odd because this guy here, for example, on the right, it's homotopic to the normal two simplex. So somehow, in the eyes of homotopy theory, we're not actually doing anything at all. These two guys are entirely equivalent. The homotopy theory can't tell them apart. But for us doing sort of these manual constructions, a specific presentation of that like homotopy type happens to be way more convenient than others. And I don't really know the good language to talk about this kind of stuff, to be honest with you. It's sort of like the meta theory of homotopy structures. So this is, yeah, something else that I think it would be cool to study more.
Just one quick question. With this Green, what's his first name? The one that didn't do anything?
That's a fantastic question. His initials are H.I. Green. I think it might be Howard, but I don't know because he actually doesn't write it on his thesis. He writes H.I. Green. Um,
Perfect.
and I know his thesis is rather hard to track down. I think Warwick University has an online copy, and that's the only copy on the internet, from what I know. So, yeah.
Perfect. Anyways, thank you again, Tim. A very
Thanks.
interesting talk. So everybody, thanks everyone. And I'm sorry, Gershom, you have a question. Go.
Just one more sort of, generalization question, which you probably don't have a great answer to, which is how much of any of this holds if you generalize by swapping out the test category? Like, could we do loose cubes or loose globes?
That's a
Uh,
really good question. A fantastic question. My claim is, I don't know, I'm hesitant to, I guess, I mean, I've already presented work in progress, so hopefully everyone knows that it could very much be wrong. My current belief is any elegant Reedy category you can do this um, for certain reasons. I believe you can do this for any elegant Reedy category. So in particular, certain shape categories, but not all of them. Um, yeah,
that's very cool. Thank you.
that's okay. Thanks for the question.
Okay. Anyways, again, Tim, thank you very much. Hello, everybody. Thank you for coming.
Thank you.
Next week we have Charlotte Attan is speaking about invariance of structures. Should be interesting. You're all welcome to come. It's going to be a Zoom call, but it's going to be at the regular 7 o'clock at night. Tim, thanks again. Stay in
Thank you very
touch.
much.
Okay.
Thank you. Okay,
Take
thanks,
care.
everyone.